ทำไมมี2นั้นเป็นสตรีมนะมาแล้ว and I don't understand why this one doesn't go. Okay, no problem. Just join this. Yeah. Join Zoom. My turn. Okay, number 2. Okay, andประภาวิทย์มาแล้วนะครับประภาวิทย์ณภัทรก็มาแล้ว moment โอเคขอเทสเสียงนิดนึงนะครับเทส 1 2 3 อัครวัตรก็มาครับโอ้ทำไมเสียงเครื่องนี้ไม่ออกเทส 1 2 3 ก็เพิ่มText 1 2 3 oh my god there's no sound at all oh connect the wrong internet I think yes we have to use NTMax and Zoom yes NTMax and okay and what is that that's the Streamlabs rate your channel okay this one too OBS number 1 okay anyway we have to send the file to iPad okay we send the file to iPad just use AirDrop and nuclear physics to iPad yes iPad yes that high to yes this one same okay andเครื่องนี้ไม่ได้ยินอีกแล้วโอเค host last is about okay test 1อ๋อโอเค test 1 2 3 test 1 2 3ครับโอเคเสียงมาแล้วwe go to GoodNote and import the file chapter 7. Oh, where is that? Oh, here. Okay, this one. It's M604. Okay. Okay. Good morning, everybody. Welcome you to SCI33206. I'm not sure where did we live last time. lecture.มีคนไหนจำได้ไหมครับเราถึงไหนกันเอ่ยhere right, this is how we control right, nuclear fission. We will start the nuclear fusion, right? Okay. Nuclear fusion. M605 has already reached several things in particle physics. Okay. Nuclear fusion is in the opposite way to the nuclear fission because they try to build up a bigger nuclei from the smaller nuclei, and the process for nuclear fusion is the following. When two or more light or small nuclei combine to form a heavier nucleus, the process is called nuclear fusion. Okay, it's a little bit, the name is a little bit different. เดี๋ยวดูครับใช้สิทธิ์จะเข้าไหมครับใช้สิทธิ์ไม่ครับ Oh, I'm sorry, I didn't share the screen. Right. Okay. Okay, nuclear fusion, right? Usually the mass of the final nucleus is less than the sum of the masses of the original nuclei, because we have beta nuclei with a greater binding energy, so that's great. The next thing is usually the mass of the final nucleus is we have better binding energy per nuclei per nucleon, so the new nuclei will be more stable, and because of the mass that is less than the original one, so there will be remaining energy, remaining kinetic energy too, and there is a loss of mass accompanied by the release of energy. That's what I have mentioned in terms of kinetic energy. 3 examples of energy liberating fusion reaction are in the following sequence. Through protons, when proton is denoted by 11p, okay, 1 nucleon and 1 proton, right? or actually it is a nucleus of hydrogen combined to form a deuteron. Deuteron is a heavier version, heavier isotope of the hydrogen, the typical hydrogen. It has one more neutron. A positron, which is denoted by E01, it has no nucleon because it's the antiparticle to electron. It has number 1 because it has the same positive charge as the proton, okay, which is the opposite to electron. Or it can be denoted by beta, okay, as you like. And next one is electron neutrino, okay, electron neutrino denoted by nu E00, okay, something like that. According to this equation, proton combine or collide another proton, we get deuteron and positron and electron neutrino. Okay, actually this one has the conservation of electron-lepton number. Yes, once we want to calculate or find the we want to find the energy remaining for all these 3 particles, we could start from the mass on the left hand side, okay, subtracted by all the masses on the right hand side at the output after the reaction, after the fusion process. Okay, on the left hand side we have 2 times the mass of the proton, right, or the nucleus of hydrogen 1,1, and on the right hand side we have mass of deuteron and mass of positron, which is equal to the mass of electron. We neglect the mass of electron neutrino, but actually it is not 0 at all. Okay, once you substitute it in terms of atomic mass, you need to you multiply with 931.5, you get 0.9315. The proton will annihilate with an electron in the surrounding to form 2 gamma rays. So yeah, we get we repeat this equation again, but we have one more input, which is electron, and finally the positron will disappear because the positron and the electron will generate the photon, okay, the gamma ray. And yeah, in this expression we could also find the remaining kinetic energy for all these 2 particles, and the energy remaining will be 1.9. okay, you substitute again the mass of the proton, mass of electron, and mass of deuteron. Okay, we neglect the mass of electron neutrino, and you will get the energy 1.9543. okay, a proton and a deuteron, in the second step of this route, especially on the sun, we have the light isotope of helium, which is helium-32. okay, we start from proton, deuteron. Okay, deuteron is the result from this one. Again, we combine with proton because on the sun there are a lot of hydrogen nuclei. So hydrogen will combine with deuteron, and it forms the light isotope in helium, which is helium-32, plus the photon or the gamma ray, right? Yes, the mass the energy could be found from the mass difference. You start from the nucleus of hydrogen 1 and the deuteron, right? The bigger version of the hydrogen, and the output is the light version of the helium-32, and you find that the energy for the photon or even the helium-32 will be 5.49 mega electron volts. Okay. In the third process, we could have two ways. The first way is that the proton hydrogen 1 and the light helium-32 combine to form the typical helium, which is helium-42, and we get also positron. And it happens according to this process. Proton and the light version of helium-32, we get helium-42, which is the typical isotope for helium. We get positron, and we get again the photon, okay, the gamma ray. Okay, if you want to find the mass difference, right, and then you combine, you multiply it with 931.5, you get the released energy for these three particles, helium-42, positron, and the photon, and we get 19.284 mega electron volt. Another choice of the third reaction, fusion in on the sun, two light heliums that unite to form an ordinary helium-42 and two protons. Okay, we start from the light versions, the light isotope, two light isotopes of the helium, which are helium-32, and we get helium-42 and two particles of proton. You could see that here you get number 6, right, in the number A, right, the number of nucleons, and on the right hand side you get also 6, okay, 4 plus 1 plus 1. And what about Z, which is the proton number? You have 2 plus 2, and right here you have 2 plus 1, which is also 4. So this equation is balanced, and if you want to find the released energy, just first compute the mass difference and multiply it with 931.5 from the Einstein energy relation. Okay, once you substitute the mass of the light helium nuclei, you get helium-32, and you get 12.95859, okay, which is the amount of energy. Okay, it's quite high, right? And the above three sequential process is known as proton-proton cycle, which is believed to be the state of energy liberation in the sun and other stars, which are rich in hydrogen. Okay, they are full of hydrogen nuclei. If you don't completely understand, just take a look at this figure. You have hydrogen nuclei, and they combine together. You get electron neutrino, right? And you get the positron, and now you have deuterium, right, which is the bigger version of hydrogen. The deuterium combines with the typical hydrogen. You get the photon and the gamma ray, and then you get the light version of helium, which is helium-32. On another side, the same process, okay, take place, and once we have helium-32 will combine together, and we will get some energy, and we get a proton. We get the hydrogen 1 and helium 2, and that's the 3 state 1, 2, and 3. Okay, 3 states of 1, 2, 3. 3 states of the nuclear fusion that could take place on Earth. All right. I hope that this might not be too difficult. All right.